I have a pendulum. A pendulum, basically, it is made of a very light string, okay, attached to an object at the end. This end is fixed to the ceiling, that end is attached to a very small object of mass m. The length of the pendulum is L. Now, you pull the pendulum to one side, let go of it, it starts to swing. Start to swing. And it goes back down, goes back up, back down, whatever. The time it takes for one complete back and forth swing is called the period P. Okay, it's measured in seconds, of course. Forward, backward, the time is P. Forward, backward, another time, T. Okay, now we want to know how P is determined by those other parameters such as M and L and so forth. Okay, so we want to determine a formula for the period P of the pendulum. That is the idea. This calculation can be done in a much later chapter, chapter 15, okay, when we study physics 1B, one semester after this, when we study what's called simple harmonic oscillation, we can actually calculate this problem, get this result. But the beauty of our analysis is that we don't know anything, pretty much. Yet, we're only in chapter 1, yet we still want to know the formula P. If we have a way of doing that, then that would be wonderful, because that means we have a way of bypassing all the detailed physics, right? So we can get to the core of the problem. How does one do that? Well, dimension analysis, that's the magic bullet. Okay, so let's look at the steps of dimension analysis. What was the first step? Okay, the first step, look at that. Identify which quantities affect your result. Okay, our result is P, of course. That's what we're looking for, right? P. We have to first know it's a function of what quantities. Okay, of course, you say L, the length of the string, that certainly matters. And what about the mass of the bob? Okay, let's put it in here. What else? Well, you know, the reason why you pull the pendulum to one side, it will swing out because gravity pulls it down, right? Without gravity, it's not going to be able to go down because it wouldn't bother. Okay, it would just stay there. Gravity pulls it down, and that's why it goes down. Okay, so what determines the strength of gravity? Well, you will learn in the next chapter. That's called acceleration of gravity, G. Okay, acceleration of gravity, G. So these are the three quantities that determine the period P. Well, to be precise, there's another quantity which also comes into play, and that is this angle theta. You pull it to one side. Now, do you pull it by 10 degrees, 40 degrees, 50 degrees, whatever? In principle, that makes a difference as well. But the problem is, if you think that P depends on theta as well, then our bet is off. We cannot use dimension analysis anymore. What's the problem? The problem is, what is the dimension of theta? Theta is an angle. What's the definition of an angle? You cut a circle, right? Theta is defined as the arc length over the radius. That's what theta is. By definition, theta has no dimension, all right? Therefore, it is just a number. It is invisible in dimensional analysis. I cannot tag it with dimension. Therefore, if this thing depends on theta, we cannot do it anymore. Well, fortunately, it turns out from experiment that as long as theta is small, okay, let's say 5 degrees or less, then the period P is not very sensitive about theta. In other words, you can change theta from 1 degree to 2 degrees to 3 degrees. P is essentially the same. So it's, as a good approximation, say theta does not matter as long as the angle is not too large. So, our first step. These are the three relevant quantities. Okay, what was the second step? Check to see if these quantities can be distinguished with their dimensions. In other words, they must have different dimensions. Okay, let's see now. What's the dimension of L? Okay, first of all, what's the dimension of P? That's T, right? Dimension of P is T. Dimension of L, length, that's of course just L. Dimension of M, that's capital M. Right? Dimension of G. Okay, G is the acceleration. It is measured in SI unit, is measured in meters per second squared, as we'll learn in the next chapter. So it's length over time squared. In other words, it's L to the first power and then T to the power -2. We'll learn that in the next chapter. All we need to know now is that is the dimension. We don't have to know details about G. Okay, now, look at this, 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 and this. Indeed, they're totally different. Okay, therefore, that satisfies the second condition. I can use their dimensions to tell them apart. They are indeed distinguishable by dimensions alone. All right, we're now ready to go to the third step. What's the third step? Here. You want to write down A as a general function of x and y, z, like this. Okay, so let's do that. So we say our function, of course, in question is P, right? I would say P is a function of L, M, and G, such that it's a constant C. I have no idea what that constant is, but I'm not going to worry about it. L to a certain power, M to a certain power, and G to a certain power. Okay, L I'm going to raise it to the power alpha, M I'm going to raise it to the power beta, and G raised to the power gamma. Okay, this is the most general way of combining L, M, and G to get P. All right, what do I do next? Let me equate the dimensions of both sides. Okay, let me equate the dimensions of both sides. This dimension, this side, of course that's this, right? The right-hand side, forget about C, it drops out. There's no dimension if I only look at the dimensions. It's L to the power alpha, M to the power beta, and then the dimension of G to the power gamma. All right? Now, what do I do next? Let me write down dimension of L, dimension of M, dimension of G, dimension of P in terms of basic dimensions, T, L, and M. These are the only three independent dimensions. Okay, so what about this? The dimension of P, which is, of course, that of time. That's just T. All right? What's that equal to? Dimension of L, that's just capital L. Don't forget, raised to the power alpha. Next, dimension of the mass, that's just capital M. Raised to the power beta. Next, dimension of G, now that is L t to the power negative 2. Okay, L t to the power negative 2, but don't forget, you raise the whole thing to the power gamma, right? So this is gamma, and this negative 2 gamma. All right. This, by the way, is m is t to the first power, the left-hand side. So this tells us t to the first power must be equal to L to the power alpha, m to the power beta, and L to the power gamma, then times t to the power negative 2 gamma. Okay, let me do some algebra on this side. What I'm going to do is I'm going to combine all the powers of L together. See, there are two powers of L, alpha and gamma. I'm going to put them together. Okay, see, if I did so, I would be getting this. T to the first power equals L to the power alpha plus beta. I'm sorry, alpha plus gamma. Okay, alpha plus gamma. Let me rewrite it. T to the first power equals L to the power alpha plus gamma, and then m to the power beta, and then t to the power negative 2 gamma. Okay, that's what I'm going to get. Now, remember, L, M, and T are totally independent. So to make this equality valid, both sides should have the same power for L, same power for M, and same power for T. Okay, now look at L first. On the right-hand side, I have alpha plus gamma. That's the power of L. What about the left-hand side? Well, there's no L, which means L to the power what? 0. Yeah, so 0 must equal to alpha plus gamma. That's for L. Okay, the powers of L must be equal on both sides, because that's how we equate the dimensions for L. What about M? Well, again, this side has no M in it, so that's 0. That side has a power beta. So that tells you beta has to equal to 0. That is for M. And what about T? Well, there is a T to the first power, so that's 1. The other side, negative 2 gamma. Okay, negative 2 gamma. Okay. So I've arrived at 3 equations. One for L, one for M, one for T. Which allows me to solve these 3 unknowns, alpha, beta, and gamma. Isn't that wonderful? As a matter of fact, this is very easy to solve. Well, beta is already equal to 0, that's given. Gamma equals negative 1/2, but alpha plus gamma equal to 0, which means alpha must be positive 1/2. So therefore, the solution is alpha equals positive 1/2, beta equals 0, and gamma equals negative 1/2. Okay, in other words, p, the period of the simple pendulum, the time it takes to swing back and forth, must equal to a constant c, I use a different color to indicate I cannot find it, okay, times L to the power positive 1/2 divided by G to the power 1/2. In other words, this is what I get. In other words, the period of a simple pendulum is proportional to the square root of its length and inversely proportional to the square root of the acceleration of gravity. Think about it. What did we really know about the system? Very, very little. All we knew is that these are the quantities, L, M, and G, that can affect the result. And then we just know the dimension of each quantity. We match the dimension on both sides, and here we get this result. We have very little knowledge of the system, yet we almost got 100% of the answer. The only thing we don't know is C. That's like 5% of the answer. But of course, in order to get that 5%, we have to do the other 95% of the work. And to find that C, we have to go all the way, finish everything we learned in Physics 1A, and we study Physics 1B, chapter 15, and that is when we find C. It turns out C to be equal to 2 pi. Okay, but that has nothing to do with dimensionalness. We cannot just get it out like this. It will be too easy. This will be done in chapter 15. Okay, but aside from that constant, we know everything about the period of simple pendulum. Isn't that wonderful? For example, we know in order to double the time it takes to swing back and forth, we cannot just double the length of the pendulum. We have to make it 4 times as long, because the square root of 4 equals 2. Okay, now let's do a little discussion about this answer. Once we know we find an answer to a problem, don't just throw it away and go to the next problem. Rather, I want you to take a look back at the answer. See if it makes sense to you. Okay? Now this particular answer says that the longer the string, the longer the period p, which means the slower it takes for it to go back and forth. That agrees with common sense. Okay, it agrees with common sense. The longer the period, the longer the string, the slower the thing goes back and forth. You can easily do this experiment and use a very short string and a longer one. You can see for yourself. Now I don't know if you have been to the rotunda of the Griffith Park Observatory. You go in the hallway. There is a huge pendulum, like 3-4 stories tall. It's called a focal pendulum and was designed to measure to verify that the Earth is actually rotating. Okay, this pendulum with such a long arm takes more than a minute to go back and forth. So that's the case of extremely long pendulum with a very large period. So that makes sense that P increases with L. Now what about G? G is the acceleration of gravity. It tells you how strong gravity is. The greater the G value, the faster an object falls under the influence of gravity. Okay, this is telling us that the greater the G value, the shorter the period. Doesn't that make sense? Because with a large, strong acceleration of gravity, the moment the bob goes to the side, you let go of it, gravity being so strong will pull it down immediately. Doesn't that make the process of swinging faster? Doesn't that shorten the period P? So you see, it makes sense that greater G results in a smaller period. Okay, one last thing here. What happened to the mass? What happened to the mass M here? Well, according to our calculation, beta is 0, so mass is gone. Okay, this side has no mass in it. Well, you cannot quite argue with our algebra because algebra is correct. So beta is equal to 0. There is no argument about that. Just because the algebra is correct doesn't mean we necessarily understood it. Okay, so does it make sense that the mass of the bob does not matter? It has nothing to do with the period. Okay, look at this picture again. This is telling us I can use a very small one, I can use a very heavy one, very light one, and yet the period of swing is always the same. Does that make sense? Even though there's our calculation result. Let's see if we can make some sense out of it. Okay. As a matter of fact, this is a special example of something very general, and that is anything that is powered by gravity. Okay. Satisfies this special feature that the motion of that object is independent of the mass. That is why, for example, everything falling under the influence of gravity has exactly the same acceleration, regardless of the mass. Okay, we'll get to the detail in the next chapter. But there is an easy way of comprehending this, as a matter of fact. Let's take a look. Okay, let's say I have, imagine, okay, I have a pendulum, right? The mass is m, right? So it swings like this, right? Like this. It takes, say, 2 seconds to go back and forth. 1 second and 1 second. The period is 2 seconds. Now, imagine this. I have a second identical pendulum, okay? Has exactly the same length, exactly the same mass at the end. These are two exactly identical pendulums. If I pull both of them to the side by the same angle and let go of it, what's going to happen? Well, they're going to swing and swing exactly in sync. Agreed? Right? They go back and forth like this. Exactly in sync. Okay, their movement would be identical. Well, if their movement is identical, let me ask you, would it make a difference if I somehow glue the two masses together like this? No, because imagine, see, if you are moving at 65 miles per hour on a freeway, right? And in the next lane, another car is right next to you, is doing exactly the same thing, is doing exactly the same, going forward exactly the same speed, 65 miles per hour. Then you can even actually stick your arms out and shake hands with the other driver. You're not going to break your arm, right? Because you move in sync, right? Same thing happened with these two bobs. Okay, they move exactly in sync. Therefore, if I tie them together, nothing's going to happen. But think about it. If you tie them together, isn't it true that you have just created a pendulum with twice as much mass? Right? That thing has twice as much mass in it, 2m. And yet the motion is the same as that. So what did that tell you? It tells you that when you double the mass of the pendulum by tying these two things together, you get a pendulum with exactly the same period. Okay, doubling the mass has no effect on the period of the pendulum whatsoever. Isn't it true then that P is not dependent on the mass? Okay, so it makes sense. All right, there are many other examples of dimensional analysis. We're going to use that a lot throughout the entire study of physics. And this particular problem is simple enough that without dimensional analysis, we can still solve it, except you have to wait for chapter 15 to do it. It turns out that in physics research, there are many situations where, in the beginning, the problem is so complicated that we really don't have a clue where to start. Oftentimes, when that happens, a good way to get things started is by doing a dimensional analysis so that you know roughly how things depend on each other, that sort of thing. So it is not just a way of solving simple problems. In fact, sometimes it provides an important guideline of solving a more complicated problem, at least to get things started. So it is a very important technique which we're going to use throughout the entire study of physics.